On this question, we want to find f composed with g of x for the indicated functions and simplify. So the indicated functions are f of x equal to 8x plus 1 and g of x equal to 4 over x plus 1. So these symbols, f composed with g of x, this symbol here is an operation on functions, and that operation is substituting one of the functions inside of the other function. So what it means is that we're going to take the function that is in front of the composition symbol, that's our outside function, and the function behind the composition symbol, that's our inside function, and we're going to do that substitution. So for this example, we're substituting g of x, which is 4 over x plus 1, into f. And when we substitute it in for f, we put it in place of the variable, because what's inside the parentheses is our placeholder for that. So we're going to put in place of that x, 4 over x plus 1. That's going to give 8 times 4 over x plus 1 plus 1. And when we multiply here, we consider that 8 to be 8 over 1 times the fraction 4 over x plus 1. And we multiply those fractions together, and you multiply numerator times numerator and denominator times denominator. So this gives 32 over x plus 1 plus 1. Now we're going to take it a little bit further, and we're going to simplify this to be in a single fraction. So we have 32 over x plus 1 plus 1, and we treat 1 as 1 over 1. And to get a common denominator, we would multiply by the other denominator, x plus 1 over x plus 1. That gives 32 over x plus 1 plus x plus 1 over x plus 1. Now we have fractions with a common denominator. We can combine the numerators. That's 32 plus x plus 1. And 32 plus 1 is 33. So we have x plus 33 over x plus 1. So we were able to work out that f composed with g of x is equal to x plus 33 over x plus 1. In this question, we're given f of x to equal negative 5 over x plus 1 and g of x equals square root of x plus 21. We want to find f composed with g of negative 5. There are a couple ways we can go about this. One way to go about this is to build or construct the function f composed with g, and then once we've built that function, then substitute the negative 5 into that function. So let's start with that way, and then I'll show you another way after that. So if we want to find f composed with g of x, we need to know what the operation of composition actually means. This operation of composition means to substitute one function inside of another function. And the way that we write it is that the outside function is the one that's written to the left of the composition symbol, and the inside function is the one that's written to the right of the composition symbol. So I'm going to be substituting g of x into f of x. So to do that, I'm going to take this function g of x, and it's going to get substituted into f of x, and it gets substituted in for this x and any x that might be in the equation of f. So that would give us the equation negative 5 over square root of x plus 21 plus 1. So this is the function f composed with g, negative 5 over square root of x plus 21 plus 1. Now that we have built or constructed that function, I'm going to be able to substitute a negative 5 into the function. That would give me negative 5 over the square root of negative 5 plus 21 plus 1. Negative 5 plus 21 is 16. Square root of 16 is 4. 4 plus 1 is 5, and negative 5 over 5 is negative 1. So we were able to calculate f composed with g of negative 5 to be negative 1. But now I'll talk about the other way you might be able to find f composed with g of negative 5. So I'm going to start with f composed with g of negative 5. And once again, I want to keep in mind what this operation of composition means. It means substituting one function inside of another function. So that means that I can write this as f of g of negative 5. G of negative 5 means to substitute negative 5 into the function called g. So into this function, g of x, I'm going to substitute a negative 5. So that's square root of negative 5 plus 21. And negative 5 plus 21 is 16. And the square root of 16 is 4. And now that I've worked out that inside part, worked out the inside, I can now work out f of 4. F of 4 means to substitute a 4 into the function called f. So when we do that, we would have negative 5 over 4 plus 1. Negative 5 over 5 is a negative 1. So we've got the same answer that we worked out in a different way. In this question, we're given a graph. I can see that this line that is labeled g of x is the red line here. And then we have a parabola that is labeled with f of x. And we can see that curve here. And in this question, we want to evaluate some compositions using the graph. We have f composed with g of 1, g composed with f of 1, g composed with g of 0, f composed with g of f of 2, g composed with f composed with g of 0. So we're going to use the graph to answer these questions, but first let's focus in on this operation composition. Composition is the operation where we substitute one function inside of another function. F, listed first, is the outside function, and G, listed second, is the inside function. So we want to substitute G inside of F, and this value here is going to get substituted inside of G. So if we go one step at a time, looking inside the parentheses, we want to find G of 1. G of 1 indicates that x equals 1. So on the graph, I'm going to find where x equals 1, and x equals 1 along this line here. These are all the ordered pairs where x equals 1. I'm interested in the one that falls on the graph of G. So I'm interested in this point here. That point has a y value of 2. So G of 1 equals 2. And now my symbols have simplified and I have f of 2. In f of 2, that indicates that x is equal to 2. X equals to 2 along this vertical line, and I'm interested in where f is at 2. So that's this point right here. So that vertical line that has x equals 2 crosses the graph of f at this spot, and that has a y value of 0. So f of 2 is 0. So we found that f composed with g of 1 is 0. Let's try the next one. I'm going to erase some of these markings. On the next one, we also have composition. So remember, composition is substituting one function inside of another function. So that gives g of f of 1. G is the outside function, f is the inside function. Let's start with f of 1. F of 1 indicates that x equals 1. So here's the line where x equals 1. I want to find f of 1. So I'm looking at the spot where the vertical line crosses the graph of f. And that has a y value of negative 1. So f of 1 is negative 1. The symbols that I have left say g of negative 1. That negative 1 is an x value. I'm looking on the graph, and this vertical line has x values of negative 1. If I look where that vertical line crosses the graph of g, that's at this spot, and it has a y value of negative 2. So g of negative 1 is negative 2. Let's take a look at the next one. The next one says g of 0. Composition is substituting one function inside of another function. G is on the inside and the outside this time. G is on the outside, G is on the inside. We want to find g of 0. This vertical line is all of the ordered pairs that have an x-coordinate of 0. I'm interested where that vertical line crosses the graph of g, and that's right here. And that is a y value of 0. So g of 0 is 0, and we have g of 0 again, that will also be 0. Let's take a look at the next one. The next one is a little bit different because we have 3 functions. We have f composed with g composed with f of 2. And when we have more than 2 functions, we just keep embedding them inside of each other. So f will be the one on the outside, then inside of that will be g, then inside of that will be f, and inside of that will be 2. So we'll start by finding f of 2. X equals 2 is this vertical line here. Every ordered pair on that line has an x-coordinate of 2. We're interested in this point here that crosses the graph of f. That y-coordinate will be 0. That's f of g of 0. f of 2 is 0. So now we need to find g of 0. I've already drawn this vertical line here with an x value of 0. That vertical line crosses the graph of g in this spot here, and that has a y coordinate of 0. The g of 0 is 0. Finally, I need to find f of 0. I've already got the vertical line at x equals 0, and this spot right here is where the graph crosses, where the vertical line crosses the graph of f, and that is at the y value of -4. f of 0 is -4. We've got our last one here. Let me erase all these markings. G of f of g of 0. So g is on the outside with f on the inside, g on the inside of that, and 0 all the way inside. So we're going to start with g of 0. Along this vertical line, these are all the points on the graph that have an x-coordinate of 0. We're interested in this point here because that's the point that crosses the graph of g. G of 0 is 0 because the y value at that point is 0. So now we have g of f of 0. Now we're going to find f of 0. We've already got the vertical line x equals 0. We're interested in this point here where that vertical line crosses f of x. The y coordinate there is -4. f of 0 is -4. Finally, we'll find g of -4. This is the vertical line, x equals -4. We're interested in this point where the vertical line crosses the graph of g. That has a y coordinate of -8. g of -4 is -8. For this question, what we want to know is the function with the graph on the right 1 to 1. So we're given this picture and we want to know if this function represents a 1 to 1 function. So I have here the definition of 1 to 1. A function f is 1 to 1 if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So what this definition is saying is that if the x values are different, the y values will be different if you have a 1 to 1 function. Whenever we're looking to determine if a graph represents a 1 to 1 function, we use something called the horizontal line test. And with the horizontal line test, if every horizontal line intersects the graph in at most one place, then we can say that that function is a 1 to 1 function. So what we're going to do is we're going to draw horizontal lines all over the graph and record how many times that horizontal line intersects the graph. And so we can see that we have this first horizontal line intersecting the graph in only one place. The second horizontal line intersects in only one place. But we do have some horizontal lines that intersect the graph in more than one place. And that's violating the definition of 1 to 1. So for a 1 to 1 function, we need different x values to have different y values. So let's take, for example, this horizontal line right here. With this horizontal line, it's hard to see with all of the vertical lines, but this ordered pair here would have an x value of -2. And this ordered pair here has an x value of about 2 and a little bit more. Let's just say 2 as an estimate. So these two ordered pairs on the graph have different x values. -2 is not equal to +2. However, when we look at their y values, because they're on this horizontal line together, they do have the same y values. F of -2 is equal to f of 2. But for it to be 1 to 1, we needed them to be different from each other. So this violates the definition of 1 to 1, and we're going to say no, that this graph is not a 1 to 1 function. The graph of a function f is given. Use the horizontal line test to determine whether f is 1 to 1. So we're given this graph here on the right, and we want to know if this graph is a 1 to 1 function using the horizontal line test. Before we do that, let's just state the definition of a 1 to 1 function. A function f is 1 to 1 if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So this definition says that if the x's are different, the y's should be different. And if that's true, then we have a 1 to 1 function. So 1 to 1 function will have different x's having different y's. And we use the horizontal line test to determine whether a graph represents a 1 to 1 function. And this horizontal line test says if every horizontal line intersects the graph of a function f at most once, then f of x is 1 to 1. So let's pause for a second and talk about why we use a horizontal line for this situation. With a horizontal line, if you think about the ordered pairs on a horizontal line, those ordered pairs will have x's that are different from each other. So I'm going to write x1 and x2. However, the y values are the same, and so when we're looking at a horizontal line violates the definition of a 1 to 1 function. So we use it as a comparison, and if we see that horizontal line crossing more than once, we know that function is violating the definition of 1 to 1. So we're looking for our horizontal lines to cross at most once so that we can call it 1 to 1. If it crosses more than once, we know it's not 1 to 1. So we're going to draw horizontal lines on this graph. And as we draw horizontal lines, we're going to pay attention to how many times the graph crosses the horizontal line. So we can see that every one of the horizontal lines is only crossing in one place. And I know it's a little bit hard to tell at the end here, but this end of the graph is consistently moving to the right and up, and so it will never repeat those y values. So because every horizontal line is crossing at most once, then we can say that this function is a 1 to 1 function. So is this graph a function? Yes, it is a is it a 1 to 1 function? Yes. Thank you for checking out my videos. Have a great day.